So we will now consider about the concentration around the medium and something called Lagrange inequality. So far we have learned about some concentration around the expectation. So Azuma's inequality shows that certain random variable, if it satisfies certain good condition, then the probability that it's far from its expectation is small. But now what we want to do is we want to consider the concentration around the median. So before here, in the previous example, how we take U, where is it? The definition of U here is defined in this way. This is almost like a median. So if we put half here, then this is more or less a median. But instead of half, you put epsilon, so it's a little bit off, but which is almost like median. So, if we adapt the proof of this theorem, then we can also deduce some, results about that. Anyway, so why do we care about the, medium is that assume we have some graph theoretic function f, and let's say you have a random graph. This has, say, median m. So I think half is not really necessary. Let's say p. Let's just say half. Then what we do is, because of this median, if we consider, all the graphs with smaller than this median value, it contains at least, give me a moment, at least half of the, all possible graphs. And if f is Lipschitz function, meaning that if you change one h, then it changed by at most 1. Then, if we have the following, if we can show that at least, say, 1 minus epsilon times 2 to the and choose 2 graphs can be obtained from a graph in this script A by changing at most t adjacency. If we can prove this, then this will imply that the probability that Gn half has a f value at most m plus t, so one side concentration. This is at least 1 minus epsilon. So see that we have certain, A, which contains this many graphs. If we see that by changing t adjacency, we can get almost all graphs. But if we change only t adjacency from a graph in here, because f is Lipschitz, the f value can increase by t. And then graph in A has a f value at most m, so we get this upper bound. And because this holds for all these graphs, out of 2 to the n choose 2, so we can show this lower bound. So here, I mean, this half is not really necessary. So, I mean, some number, say epsilon times this many, at least this many graph, I mean, or other, I mean, this, if this is too small, then we cannot really show this. So, but if we can, as long as we can show this with a certain t for Lipschitz function, then we can show, I mean, this concentration with, I mean, this doesn't have to be really median. If we have a m prime which satisfies this condition, then we can still show this, I mean, m prime, this inequality with m prime. Anyway, so as long as you have a non-negligible term here, then this number must be very close to median, more or less median. So this approach might, I mean, provide some, I mean, concentration around the median. At least, I mean, one-sided one. But you can, I mean, kind of do it twice to make it, I mean, make it two-sided concentration. Anyway, so on here, so again, the, I mean, important thing is that this random graph is a collection of, I mean, collection of independent random variables, and we are changing at most t coordinate here. So we can actually generalize this setup into the following. So we have, say, n be the number of vertices in GNP, choose 2. So here we consider n as the number of vertices, but we want to now consider n as the number of coordinates. And we consider subsets in of n. Or this subset is same as 0, 1 coordinate vectors, which is in, which has n coordinate. So 0 means h is chosen in the, h is not chosen in the random graph, and 1 means h is chosen in the random graph. So this setup is actually more general than random graph, considering this each one of them as a, I mean, same as being h there or not there. And here what's related to this changing adjacency is Hamming distance. Hamming distance between, I mean, 2 points, x and y. So this is x, then x. This is first coordinate x1, and this is second coordinate x2, and so on. X and y is Hamming distance. Let's say rho of xy is summation of, I mean, it's same as number of I, such that xi is different from yi. So this measures the how many adjacency we have to change in the random graph model. And now let's say B. So for given A, which lies in 0, 1 to the n, let's say B, A, S, all around A with this, I mean, radius S is a collection of points which has Hamming distance from X is bounded by S for some A. Then, I mean, we can actually apply Azuma's inequality to prove the following. So let lambda be positive and epsilon be the e to the negative lambda square of 2, which is what, I mean, number which is familiar with us because we have used in the previous example, previous theorem. And say let A be a subset of these points which contains at least epsilon times 2 to the n many. So epsilon fraction many of points. Then we have that all around S with 2 lambda square root of n contains all points except epsilon fraction. So the proof is kind of using the similar approach as before. So we choose say point G in 0, 1, n uniformly at random. Then for each y, let xy be a random variable which is the distance from y to x. And we consider martingale, x0 to xn be martingale, which is exposure martingale, exposing one coordinate of G at a time. So give me a moment. Meaning that the xi expectation of xg, where g1 to gi coordinate are exposed. Then you can check that if we have y and y prime, which is differ in only one coordinate. So we check the Lipschitz condition, and with this setup of exposure martingale, we can apply Azuma's inequality. We use this Lipschitz condition shows that this xi and xi plus 1, the difference between them is at most 1. So by letting mu be the expectation of x, what we know is probability that x is smaller than mu minus lambda square root of n is smaller than e to the negative square root of 2, which is epsilon, and probability that x is bigger than that is again smaller than epsilon. But what do we know? By our assumption, A itself has a large size. So whenever our chosen points G lies inside of this A, then x becomes 0. So probability that x becomes 0 is A size of A over 2 to the n is at least epsilon. So this implies that mu is at most lambda square root of n. Again, you use this to plug into the second inequality. Then this happens, the x being bigger than 2 lambda square root of n is smaller than epsilon. So our choice of G is uniformly at random. So this implies that if we take a ball around A with a radius 2 lambda square root of n, then this is nothing but 2 to the n times probability, this probability. Not this probability, but this complement probability. So we get this. So this proves the theorem. So if we write B of S as the ball of radius S around the say origin, where the distance is measured by the Hamming distance, then the above inequality can be rephrased at the, for certain value r, we have this implication. So this kind of shows that taking A as a ball is the way to minimize the, number of points, while its ball around it has also minimum volume. So meaning that when set A is given, then if this is not a ball itself, so A is given but A is not ball, then we take a ball around this A. Then the volume of that itself is also, not really minimum, in the sense that taking ball has among the same volume. If you take a ball, then you take a ball around ball, then that has the minimum possible, volume. So it's kind of isoperimetric inequality for, say, r not so smaller than n over 2. Because r is close to n over 2, then this has size half times 2 to the n, and it's a bit smaller than, we can ensure this inequality, but if it is much smaller than that, then we cannot really ensure that. So this theorem implies that. But it is known, actually, that, say, Harper, actually, it is known that it is true in general. For all RS. Anyway, so we have proved this result, which can be kind of considered as a concentration around the median in the GN half case in terms of this Hamming distance. But we can ask ourselves a question. So in lots of applications, Hamming distance is not exactly what we want. Because let's get back to the graph example again. Let's say we want to consider some random graph, random variable. Let's say x is the number of size of largest, let's write it this way, the largest number of H-disjoint clicks of size k in a graph G, where G is drawn from G and P. Let's say this is the random variable. And let's say you have a k equal 4. You have some graph G drawn from here. So again, this can be identified with points where we have many coordinates, and then each coordinate corresponds to some pair ij, and then this is 0 or 1 depending on whether there is an edge or not. So here, obviously, not obviously, but let's say this is the maximal collection of edge-disjoint k clicks, and let's say this is a unique one. So every other edge-disjoint k click you take, it has a smaller number. Here, if you change the adjacency of this, or change the adjacency of this, then x does not change. But if you change the adjacence of this, then x might change. And let's say this is the case. And if you also say change the adjacency of this, then x change. So these edges and these edges are not really same. Meaning that some edges are more important and some edges are less important in terms of measuring this x. So in other words, now we are considering this Hamming distance, and some coordinates are more important and some coordinates are less important. It could be the case in some application. So we can ask that maybe we can exploit this to get some theorem which can exploit this fact to get a better concentration, or it becomes more efficient to use it in some application. Give me a moment. So we want to better, cope with this kind of situation. What we can do is we can introduce the following more general setup, and then consider the similar inequality regarding the previous, like the ones that's used here, the concentration around the median. So let's consider this setup. Let omega be again we will make it more general. Omega is the product space where this omega I is a probability space. And this omega has the product measure. And let A be a subset of this omega, and let X be the some vector, which is a point. So which has n coordinates, and each of the xi is in omega I. And so as explained before, depending on the application, some coordinate might be more important and some coordinate might be less important. So motivated by that, we define the following following definition. Let's say rho of A, comma X be the least value such that for any alpha, so alpha is a weight, so this is weighted Hamming distance. So alpha is weight, which indicates how important its coordinates are. So which is a vector with length 1. So when weights are given, weights on each coordinate, which one is more important and which is less important, and we consider the worst case scenario. So for this specific weight, so you have A here, and then let's say weight is given, and according to this weight, you want to excuse me, you want to measure the distance between X and A. Simple way is you use the Hamming distance, and then you measure the Hamming distance between A and X. With respect to the Hamming distance, you find the Y, which is close to X and that distance is the distance between x and a. So when distance is given, you choose y, which is close to x. You choose y among a. The distance is the distance between x and a. But instead of having distance, now you consider this distance. So these weights are given, and xi and yi are, so you count the coordinate which is different between x and y. So you can choose y from a, which is best for you. And between these two, you consider the coordinates which are different. But for each coordinate, we have a different weight given. So some coordinates are more important. So difference in there contributes a large number in distance. And some coordinates are less important, then coordinate there contributes less on that coordinate. That distance. Contributes less to the distance. So you add up, then that's the distance. And among those, you choose the maximum so that this weighted distance is the least value satisfying this. So no matter how these weights are given, so it depending on situation that we want to consider. So this could be badly given, but if you can choose y so that under this metric, x is still, the distance between x and y is still at most this number. So among those, you choose the smallest one. So that's your, weighted Hamming metric. And for any real t, let's say let a t be the points in this probability space where it's close to a. The distance between x and t are at most, x and a are at most t. So now with that, we will show later on this Lagrange inequality that for any a, we have that probability a, the measure of a, minus 1 minus probability of at is more than e to the negative t squared over 4. So once we have this, and then how we apply it is that we let a be the, so let's say we have some f. So this is collection of, say, x whose f value is smaller than its median. Then probability of a is bigger than half. Then how do you get it? What do you get it? Then probability of at, 1 minus at is just some constant times this small. So you can actually show that the concentration this shows that with high probability, with probability at least this, the f of x is at most median plus t. Similarly, you take, so this provides a concentration from above. Similarly, you can actually take a so that the take a and t so that this probability of at is around half. Let's write it in more rigorous sense. Let's say a is probability, the set of all points, f of x is smaller than m prime, where m prime plus t is median. For certain m prime and t, we can make sure this. Then this is roughly half. Then probability of A is at most 2 to the this. This shows that the f of x is with high probability, at least m prime, which is median minus t. So this provides the concentration around the median. Of course, in here, this distance is defined in this way, the weighted Hamming metric. Among all the weights, you take the worst one. Anyway, with this, we can actually later, apply this to several, problems. So next time we will prove this Lagrange inequality, and we will also see some application of this.